Hello, everyone. How's it going? My name is Alex. I'm from Fluence. I'm a developer myself. Been team leading the network team on Fluence. And today I'm going to talk about what makes Fluence, how it works, how to use it. I'll try to show a little bit of experience of how it might look for developers, even though we have static slides here. Okay, so Fluence is composed of three main components. That's Compute Marketplace. That's a two-sided marketplace, where on one side are the compute providers that provide hardware and those compute resources. And on the other side are developers who consume those resources by deploying applications to the hardware. And those applications they build with the cloudless stack. So Compute Marketplace is a place where providers set their prices and say, hey, I'm ready to serve your workloads for this price, and developers discover that, and there is a natural competition over hardware prices and over different services provided there. So let's talk more about the Compute Marketplace. It's a global network of providers. Right now, we mostly target the enterprise-grade hardware, because we are to replace enterprise-grade clouds that have high uptimes, good disks, good network connection, fast CPUs, and overall provide good experience and ability to build enterprise-grade software. That's in contrast to commodity hardware that's often been the focus of the DePIN sphere of this industry. We're thinking about that too, but our current focus is on providing a seamless experience to developers, to users, so they can really build complex projects that require high SLAs. In order for providers to be sure they can pay their bills and their income is stable, we made the protocol in a way that allows developers to pay with stablecoins. So developers, when they deploy their workloads on the provider's hardware, they pay for that in different stablecoins. If we consider a possibility for them to pay, for example, with our native token, with FLT, that would make providers kind of dependent on the fluctuation of the price. And if the price goes high, then providers might overcommit on next investments in their infrastructure. And when the price normalizes, they will not have enough income to continue supporting that infrastructure. So that's why developers are paying for their workloads in stablecoins. However, in order for the network to make sure that there is enough capacity, idle capacity, to accommodate more and more workload for from developers, we need to make sure that some of the providers stay idle and not saturated by the existing workloads. And for that, the protocol gives FLT rewards for providers that are idle and can prove that they have enough CPU capacity, enough disk and RAM capacity. I'll talk about how those proofs work a little bit later. But you can see that there is two streams of the income, the stablecoin and FLT rewards. This network is not homogeneous, so all providers are different. In what differs them, besides the amount of compute resources they provide, is the managed services. The Fluence allows to integrate basically any software into the protocol, so it allows to connect different Web3 protocols, be it IPFS, Filecoin, Ceramic, and others. Or it could be like Ethereum RPCs, different Web3 protocol APIs, or it could be Web2 software like Web2 databases, be it Postgres, Elasticsearch, or be it some network API that you want to call to send an SMS or something like that. As long as there is a network API or CLI API, it's possible to integrate that into Fluence. And that makes different providers different, because they decide, I have expertise in providing Redis, for example, and I have expertise in hosting Filecoin, so I will provide API to get data from Filecoin and stuff like that. The way we measure the computation in Fluence is by using the compute unit. That's an abstract unit of computation. It corresponds to one physical core. It's important to see that for CPUs with hyperthreading, it's going to be 2 logical cores, and on other CPUs, it's going to be a single core. But in essence, it's one physical core, 4 GB of RAM, and 10 GB of virtual disk for storage. Providers operate not just in terms of CUs, but obviously in terms of physical hardware, so of physical servers. And each server participates in the Fluence peer-to-peer network, exchanging network packets, participating in the discovery protocols and stuff like that. So when a provider registers a certain peer, a certain server in the network, it provides many compute units. Number of compute units in a server roughly corresponds to number of physical cores. So for example, for a machine with 64 cores, there could be 60 or 62 compute units, depending on how providers set them up. Usually, we advise our providers to leave 1 or 2 core for needs of operating system. So it can do scheduling, it can do I/O processing, it can do network processing. So depending on the workload that providers observe, they might change those numbers. So every compute provider would likely have many different servers with different number of CUs, and they would register them all together. You can think of every compute provider as a small or big business that wants to utilize their compute resources to get money in as stablecoins or get money as FLT. As I mentioned before, it's important for the network to be sure that there is enough compute capacity, idle compute capacity in the network to accommodate new workloads coming from developers. So when you, as a developer, want to deploy something, for example, on Amazon, you can be sure that there is enough capacity for your workload. That's exactly what we want here. And for that, we employ the mechanism called proof of capacity. It's basically proof of work. It runs in a way that how many idle CUs are there on a server, that many randomX threads will be run on that machine, saturating the cores completely, eating out 4 GB of RAM, and thus proving that those CPUs, those cores really exist and really are not shared for any other workload. So on a single server, it could be that some compute units are dedicated to calculating proof of capacity, and yet others compute units are dedicated to so-called useful workload, the workload created by developer for which they pay in stablecoins. Every CU is required to have a stake on it, so provider has to put a certain amount of FLT tokens so that when the provider stops sending proofs suddenly, for example, because of the downtime, it can be slashed, that stake can be slashed. And obviously that the FLT rewards that provider receives or delegator of the stake receives, because it's possible to delegate the stake, are proportional to the number of CUs. This protocol is tolerant to providers' downtime, so as long as provider doesn't have much downtime, it's not going to be slashed, but the downtime is accumulated over time. So if provider goes below its SLAs, it's going to be slashed. Yeah, and as I said before, compute units can switch from calculating proof of capacity to serving developer workload, the cloudless functions. And that happens in a way that each server of the provider listens to the events from the blockchain, and when it receives a signal like hey, please stop sending proofs for that compute unit and instead deploy those WebAssembly functions, those cloudless functions to orchestrate them. Provider does exactly that. So every server can have, in different moments of time, can have different CUs allocated to useful workload and different CUs allocated to calculating compute proofs. Providers might balance that. They might have different strategies. It's a free open market after all. So they might experiment with different proportions and different prices, regulating those proportions. FLT rewards that are received for putting stake and sending proofs by providers are vested. That incentivizes providers to stay in the network longer and longer, because if they want to stop serving their capacity, stop sending proofs, or stop participating in the protocol completely, they will only receive the vested part of the rewards. That makes certain pressure for them to keep their hardware in the network indefinitely. So let's talk about the cloudless stack, the SDKs and approaches that allows developers to build distributed systems on Fluence. So the central concept here is the cloudless function. Cloudless function is the orchestrating mechanism or choreography mechanism. It's a workflow script that tells, hey, go to that peer, execute that function on that peer, take the data, put them to variables, send to other peer, and overall it allows to describe any kind of distributed algorithm. But in essence, it's a thing that orchestrates WebAssembly functions. So that, I hope that's visible. That's how it looks for the developers. If they are to use Rust, they would write code like that, just the usual Rust code, and you put Marine macros on top of it. Marine is our WebAssembly runtime. And for example, here you can see they can issue HTTP requests as long as provider allows curl effector, like curl managed service, to be deployed on his hardware. After developer described that algorithm, she compiles it to WebAssembly. Then she provides a deployment definition, deployment configuration, saying that for curl deployment, that's just a name, I want replication factor free, that's target workers, and I agree to pay 0.33 USDC per epoch per 24 hours for that. And it includes just a single service, and you can see spells there. That's our analogy to cron jobs that allows to run cloudless functions by timer or by some event, and thus orchestrating something that happens in background on its own. After deployment is created, you can see there is a succeeded deployment. That's how it looks. You can see a corresponding contract that describes the deployment and manages the balances. On the blockchain, all the computations obviously happen off-chain, but the descriptions, the accounting, it happens on-chain. And you can see that replication factor was free, and now free workers joined that deployment, and from that point on, it will slowly start taking balance from the deployment balance and sending the money to the providers. And it's reachable by the network by using the cloudless functions. So cloudless functions are written in a language developed by Fluence. The language is called Aqua. It's not a general purpose programming language. It's a workflow language that allows to describe distributed algorithms of any kind, but it's pretty small. So it's not, as I said, it's not a general purpose programming language. It just has enough constructions and tools to allow to describe distributed workflows. Here you can see that it's just a function, so it could be used as a library. It's abstracted over peers that participated there. And here it implements part of the threshold signature protocol in multi-party computation setting, where we are asked, or rather providers are asked to go to that array, that list of peers that participate in the threshold signature cadence, and iterate over them in parallel, and go to every of them and call first the function called getKeyShare, then call function called getRank, combine those results into response, construct the algebraic data type, and return it back to the caller. You can see that by the putting par there next to the 4, we parallelize the computation so that workflow happens at the same time, concurrently and in parallel on all the peers that are described by TSS parties. It's executed like that. Every peer in the network, like cloudless functions are executed like that. Every peer in the network has an interpreter for the cloudless functions. So it's kind of executed between the peers in a sense. It's not executed on some specific peer, it's executed on every peer where it reaches, and it's self-routing. So every peer in the network, even the browser peers, they know how to interpret those cloudless functions. So wherever it arrives, every peer can just read the script and see, hey, this line is not for me. I know for what public key this line of the script is, so I will route this cloudless function to that peer, and when it arrives to the first correct peer does some function calls, resolves where to send them further, and does that. And this is self-routing execution, which just sent to the network, replicates, forks, joins, goes in parallel, sometimes, and it's up to developer to describe the distributed algorithm she wants to see there. If she wants it to be a request that goes through 100 of peers and then back directly to her browser, she can do that. If she wants that just to be a request, like a cloudless function that goes through 100 peers, writes some data to them, she can do that without returning the result. It's pretty flexible and allows to do many, many things. And as I mentioned before, providers are differentiated by different managed services that they provide, and cloudless functions allow to be integrated with different protocols, be it storage, blockchains, Web2 APIs, or databases, Web2 or Web3. As long as it has network API or CLI client, it's possible to integrate it into Fluence, which is virtually everything. Along the execution of the cloudless function, all the providers, all the peers that participate in the execution, they put their signatures, so you can, as a result, that network packet that brings the cloudless function, it also brings with it a trace of execution, and it's basically an auditable log of what function was executed with what arguments, in what order, and it's possible to compare that audit log with the cloudless function and see if it was executed correctly. So that gives you kind of a proof of that network framework, of that order of execution and of the arguments that were used. So you can certainly say that this computation was called with those arguments and what produced those results on certain peers. Aqua, the language behind cloudless functions, allows to implement basically any distributed algorithm. So be it consensus, be it failover, quorum, multi-party computation, lots of them. How much time do I have? Okay, 10 minutes. So yeah, and that's the Fluence network. Lots of providers in data centers with good uptimes, providing integrations to different services. Everything is paid by stablecoins, by developers. There is enough capacity to accommodate workload, and as the demand grows, there's going to be more and more capacity because token is going to be more and more interesting for providers. So, yep. Let's take a look at the software architecture behind the protocol. So first, let's see what constitutes a single compute provider. You can see here that it's a capacity prover. It's a software that runs randomX and saturates the idle cores. It's Nox. It's the Rust implementation of the Fluence peer. I'll show its architecture in detail too. And those two basically constitute a complete Fluence peer. So complete Fluence peer is a prover and a Nox. Together, they constitute the capacity proving and the network part and the function execution, the WebAssembly runtime. I'll go to that into detail a bit on the next slide. So some of the providers also participate in the validation of the blocks of the blockchain, of the L2 blockchain that powers the billing, the proof verification of the Fluence protocol. Some of them don't. That's like a decision of the validator and of the protocol. Right now that L2 is on proof of authority. It will be on proof of stake pretty soon. The provider, if he or she has a validator or not, it's connected to the L2 blockchain powered by IPC blockchain. And finally, it's parented to Filecoin, be it calibration for testnets or mainnet for mainnets. So the Fluence peer architecture is like that. You see there are two implementations here. First one is the Rust implementation. That's the peer that's meant to be run on server hardware. It contains Cloudless Functions interpreter, it contains WebAssembly runtime, and it's powered by libp2p. On the left, you can see JavaScript client. It's meant to be used in browsers or in CLIs or like in any front-end software. And it has basically the same architecture. It's a bit lighter, or it's much, much lighter because it's not meant for high load, and it's not participating in the Kademlia protocol. Only Rust peers participate in the Kademlia protocol. That allows them to discover each other, and they're long-living. That's why it makes sense for them to participate there. JS clients connect to the whole network only through Noxes, through Rust peers, and they use them as relays. One big limitation of JS client being that it's impossible to connect there because it could be behind several nuts. When you're sitting in McDonald's on some Wi-Fi, you cannot just accept any incoming connection. The firewall won't let you. So you need some connection to the network that allows for two-way communication. So the billing, the proof verification, and tokens and all the smart contracts, they live on the IPC subnet, on the L2 blockchain. And you can see what it has inside. It has the compute marketplace, that the smart contracts. It has a proof of capacity verification. It has FLT bridged from Ethereum to Filecoin and inside IPC. And it has a wrapped USDC and other stablecoins that developers can use to pay for the workload. Yeah, the token, the FLT token, is bridged from Ethereum to Filecoin and to the L2, to the IPC. We use Axelar as a bridge to Filecoin, and then we bridge them further to the IPC itself. Right now, we have two main networks. Like there is a mainnet that's called Cross. It's parented to the Filecoin mainnet, and it hosts. It works on real tokens. It works on real FLT, on USDC. We have external providers and onboarding more and more of them. We have an on-call team that guarantees uptime of that network. We guarantee version stability, and we make sure that if we are updating something major, we notify people about that. Yeah, so it's a stable, the stablest network that we have. The second important network is DAR. It's parented, it's a testnet, so it's parented to Filecoin testnet, the calibration. It uses testnet tokens, and mostly it's for hackathons and developer UX tests. We're thinking about maybe making that the network for the commodity hardware, so we may switch to real tokens there, or some other tokens, but still the ones that have value, and not just test tokens, and bring more and more commodity hardware there. So the cross then would be the mainnet with high SLAs, and the testnet would be a much bigger network, and it wouldn't be a testnet anymore. It would be a mainnet, but it would not provide as high SLAs, as high uptimes, and as high quality hardware as the mainnet. And we have a stage for wild tests for providers to come and register themselves, so it might not work at times. That's the goal, to break it. So please come and break it. So if we see at the developer tooling, there's actually lots and lots of developer tooling that we have inside of Fluence. We have Rust SDKs, JavaScript SDKs, we have programming language, we have a compiler for that programming language, we have VS Code extension, and different IDEs are coming as well. We have so many things, but they all are packed to the Fluence CLI. That's our Swiss Army knife tool for developers to deploy their code, to inspect it, for providers to register on the network. Go and explore it. It's a pretty nice. The UX there is great. We make sure that the UX is great, because it's so hard for me personally when some Web3 tooling just gives you some error, and you don't know what to do with that. And we care about making sure that when users encounter something unexpected, they surely know what to do next. The documentation for the project lives at the fluence.dev. Soon we will open the stage for anyone to register their providers, so you can experiment, because right now it's on the cross, on the mainnet and testnet, it's permissioned. We want to open it on stage so people can experiment with their software, with their strategies and stuff. We have a Network Explorer. That's the screenshots, the white ones that you see. That's from the Network Explorer. You can see we have different providers registered on mainnet. They have different offers with the same price right now, but they can change it. It was their choice, with different number of compute units, different number of peers. So we're evolving there. So what's in the future for Fluence? We plan to go for AI. So right now the compute units, they are tied to CPUs. We want to make it possible to have compute units on GPUs as well. Right now we're mostly focused on Rust, but we want to provide more programming languages, and Python and JS are what we hear from people are the most important languages. For that, we want to provide ability to run Docker containers, and we're designing and implementing that. We want to get further into the proofs of what's happening on the network. So right now it's proof of capacity, it's those audit logs, but we want to also have proof of compute, so we can prove that certain WebAssembly functions or any other runtime functions were executed correctly. Probably that's going to be zero-knowledge solution. We want to provide a market for liquid staking. Right now it's possible to, for one entity to put stake for the provider, so it could delegate its stake, and that makes it possible to trade that. We want to integrate trust execution environments, that's TE, so people have easier time storing secrets and managing secrets on Fluence. As an alternative to that, we will provide MPC subnets, multi-party computation subnets, so private keys can be shared, for example. It seems it makes sense to integrate fiat payments, so people can pay for the hardware, for their workloads with credit cards, and it would make it easier to onboard more and more people. We're looking into more and more data integrations, not just IPFS, not just Ceramic, not just Filecoin, but more and more some S3, some Web2 databases. There's just really many possibilities for that. We're going to be switching the proof of authority mainnet and testnet to proof of stake soon. And also I wish to see a GUI for Aqua, so it's easier to draw distributed algorithms instead of programming them. I like programming them, but not everyone do. And last but not least, we have an airdrop. So if you ever contributed to some Web3 projects, you can go and check if you're eligible. You go to claim.fluence.network, you enter your GitHub username, and you see if you're eligible. And just make sure that your SSH keys were published on the GitHub like 3 months ago, or because if they weren't, the airdrop, it's trustless, it doesn't use any centralized oracles. So, but it requires you to have SSH keys published for your GitHub account at the time we made the snapshot. And that's it from me. If you have any questions, I'd be happy to answer them.
One question. Does anybody want to ask the one question we have time for? Anybody?
Can you hear me? Yeah. Thank you for your lecture. So, do you envision that one day, since it's a decentralized and distributed computing power, that there will be people who will organize compute farms, like, I don't know, many servers working for them? And do you think that, do you have any way to prevent them making, being a single point of failure?
Mm-hmm.
Thanks.
Yeah, thank you for the question. So what we envision regarding the people organizing themselves into big compute entity is one thing are the DAO regulated DAO paying for the infrastructure for certain companies. So it's possible with Fluence to automate payments for the infrastructure. You just make like a proposal on your DAO and say, hey, pay the Fluence DAO certain amount of money, create a deployment, pay for that infrastructure, and this way you can power infrastructure of your business or of community-owned business through Fluence. Regarding the big creation of big farms that become big single point of failures, it's possible for developers to specify different filters when they provide their deployment. So it's possible to also specify the geolocation of those of the providers. And I think it's got to be super easy to just add many of them, many geolocations, and say, for example, I want replication factor of 17, and I want that to cover 4 different geolocations. So, and that would basically solve that problem. So if there are some big farms in different places of the world, still a single deployment would scatter across all of them.
Amazing.
Thank you.
Thank you so much, and please, big round of applause for Alexey with Fluence. Can you guys believe that this was his first ever big keynote? Thank you so much.